The next talk will be given by Bruno in person here. Do you need some help with setup? Maybe Ignacio can help with the setup.
I think it's this computer, right?
Yeah, I think it's already on the desktop. So, right.
So we just need to share this. Yes.
Okay, you're all set?
Yeah.
And the floor is yours.
Thank you. Thank the organization to give me the opportunity to present here. I presented last year on the former OpenMolcas meeting online, and this is my first time presenting in person. So I'm kind of new to the OpenMolcas community. I'm a postdoc at DTU, Denmark, in the group of Sonia Coriani. And my postdoc project is around the process involving the promotion of electron to the continuum. So my title is Photoionization and Auger Spectra from RASPT2 and DFT-Bspline Bound-Continuum approaches. All right. So I will present my recent developments using OpenMolcas, aiming at the observables. My whole presentation is about spectroscopy. Observables involving the promotion of electron to the continuum. So the process is very basically represented there by an initial state, the phi I of n electrons, and at the end you have an ion state of n-1 electrons, a k final state, and the electron in the continuum, right? And the processes, the observables that I'm interested in, they are the photoionization press sections, double core hole shake-up spectra, and resonant and non-resonant Auger spectra. All of these properties, they involve the promotion of electrons to the continuum. Right. So the basic idea of my procedure is what I try to reproduce in this illustration, quite naive hand drawing. So, but in blue here, I have the pieces. So the idea is to divide the electronic problem in the pieces where I can treat at the RASPT2 level using the basis set, the common basis set of Gaussians that we are all familiar with. And I leave the electron in the continuum to be treated in an external code using different boundary conditions. The problem is that the molecular part, the initial ground state of the cation, they have different boundary conditions that the electron in the continuum that oscillates to the infinite, right? So here, this is my color code for my whole presentation. In blue, I have the pieces that I get from OpenMolcas using the Gaussian basis sets. And in red, I use this multicentric B-spline representation at the DFT or the DFT levels, right? The basis is represented by this piecewise B-splines and the spherical harmonics. And I get that from external code developed in Trieste by Professor Piero Decleva. So for now, assume that I have access to this continuum wave functions from external code. They are pretty accurate, right? And I will focus my presentation on the bound part. And at the end, if everything goes right, I can put them together on the final state wave function by an anti-symmetrized product of the two parts. The two pieces. All right. So the first property is the photoionization cross section, normally represented by this single sigma. You have here a bunch of constants and the dipole matrix elements. Right? And the dipole matrix elements, since I use different basis approximations, I compute them numerically. So I get the continuum wave function. And here I have the overlap, the dipole integral involving this quantity here. And the quantities in blue, they are the ones that Sergey already introduced to you in his talk on Thursday. They are the Dyson elements, or the Dyson orbitals. So this guy here, the Dyson orbital, you can think of as some kind of reduced one electron transition density matrix. And the conjugate Dyson orbital, which enters this piece here of the expression, they are kind of reduced two electrons transition density matrix, right? And so then putting it together and integrating numerically, and we have what it is needed to compute the photoionization cross sections. An important thing to mention about it is that if you are dealing or if you are aiming at the photoionization of valence states or single core states, you can just forget about the second term. It is really negligible. Don't worry about it. This will be the important and the relevant pieces. But for the only for the relevant and exotic case of double core holes, this becomes important and even sometimes more important than the what is known as the primary term. And it happens to be my interest in this. I have interest in this exotic example of the double core spectrum. All right, but before showing you a practical example, just to explain briefly what is this double core spectrum, you have also the pre-edge and the post-edge region. The pre-edge region, you can think of it as a super satellite of a single core hole state, right? And you have two distinct channels for these processes of the double core hole shakeups. You have the direct channel and the conjugate channel here in this chart. So the difference is that in the direct channel, you have a dipole ionization and a monopole shake-up excitation. The conjugate channel, you have a dipole core excitation and a monopole shake-off ionization. And the interesting thing is that these two channels, they follow different selection rules, and you can identify them in the spectrum by these different selection rules. A practical example is this. This is the pre-edge K-2V spectrum of the carbon monoxide. And the dots here are the experiments from 2021, so pretty recent experiment. And if you do like you would do in the valence and the single core approximation, you would take only the direct term, which is the first piece there. Okay, now the selection rules that you have, they are the monopole selection rules. So you only see the direct, these peaks here in blue, but parts, and I mean, a very important part of the experimental spectrum is completely dark if you take only the direct approximation. But now if you do the full approximation and you take the direct plus the conjugate part, now this is the conjugate channel. And so only when you consider the full approximation using the direct one particle of the conjugate two particle Dyson orbital is that you can also actually reproduce the spectral properties of the experiment, particularly this guy, right? So this is a very interesting example of the application for this K-2V spectrum. And now another process is one of the major spectroscopic measurements that we have since its introduction is the Auger decay spectrum. It's a different thing, but also involves the promotion of electron to the continuum, right? Just for the ones not familiar with the Auger process, so it is a decay when you start from a core hole state. So the initial part of the Auger decay is promoting a core electron. You can either ionize or excite. When you excite the core electron is what we call the resonant Auger, or when you ionize, you just remove this electron. This is the normal Auger. They follow the same idea, the same properties. So I'm illustrating here only for the resonance case, right? So you promote this electron. So this electron is here, and you have two decay channels. In this panel here, the first decay channel would be the participator Auger, and the participator, as the name already says, this promoted electron will participate. So this would be the one ejected to the continuum. And you have a decay of a valence electron, which will fill the hole in the core level. The other channel is the spectator Auger decay. So as the name already says, is a spectator. So the excited electron would be there as an spectator. And the decay, the other valence electron filling the hole and the ejected electron, they are on the valence shell. And the particular property of this kind of channels here is that you are left at the end with a two-hole, one particle, or even three-hole, two-particle configuration. So you actually need some electronic structure method, which is flexible enough in terms of excitation space to reproduce this guy here decently. So that's why RASPT2 is a perfect candidate to reproduce Auger spectrum. And so I had to in this slide here, just in very little detail. I don't want to spend so much time. Sergey already mentioned that in his presentation, we use the Fermi-Golden rule to connect the initial state to the final state via the Hamiltonian operator. Just notice that in this case, the initial state is the core hole, it's not the ground state, right? So after a few manipulations, we can get to this expression here. And I highlight in blue these matrix elements, which you could recognize from the beginning of my presentation. These are the Dyson matrix elements, the one particle and the two particle Dyson. So since I luckily already have them implemented, so it's just working here. This is the one particle Hamiltonian, and this is the two electron integrals, the Coulomb term. So we're halfway. So all right, but there is a little problem for these two electron integrals. We have here the integrals involving the electron in the continuum. And in the first approximation, we can forget about the one electron part, which is of small importance. This is the overwhelming term. So we have at this point two ways to go. One way is to compute this numerically after having the wave function of the continuum. Okay, this is something that we are working on, right now, but there is a little problem with that because you have to interface different codes, different boundary conditions. So you kind of rely on an expertise that generally quantum chemists don't have, which is the expertise of the continuum, and these codes, they are really difficult to use. So the best thing would be to have something that one can compute the Auger spectrum directly from a code like OpenMolcas without this burden of interfacing different codes. And we could reach that in this publication recent with the participation of also of Sergey, with this 1 cent approximation method. And the 1 cent approximation is kind of an old approximation. It goes back to 1975 and also very well exploited by Ingolf Fink in the 90s and 2000s. So the basic idea to deal with that without needing to explicitly compute the continuum wave function is to use this pre-calculated atomic bound continuum to electron integrals. Basically, very basically, right? It's more complicated than that, but it's basically like you project your problem, your decay problem, to the problem of an atom, an isolated atom. And you do that for the integrals, but you keep the molecular properties here on these matrix elements. And since you now project the problem in an atomic problem, I mean, the atomic integrals, they are the ones that you don't have to compute every time you change the system. They are computed once for all. So you keep them stored in the program. I mean, it doesn't matter if you are computing the Auger decay for the core decay of the water molecule on the oxygen edge, or is the oxygen edge of uracil, or oxygen edge of whatever molecule it is. The atomic integrals, they would be the same from the atomic oxygen decay problem. The only part that will change and we have to work on is the molecular problem. So going straight to the applications and to see if this implementation also works, is to check here some calculations with experiments. The experiments here in the bottom in red, and the calculations here on the top. The neon is the atomic. This is just that case just to check if I did everything right, because for an atom, the 1 cent approximation is already the full approximation. So you see that all the features from the experiment, they are reproduced here, looks fine. But I mean, this was already expected. And the interesting part is to check how it works on a molecular problem. This is a very simple problem, a diatomic molecule, carbon oxide, but the carbon edge and the oxygen edge. Just visually comparing what you see on the calculation with the experiment, looks like we're getting all the features, all the proportions, everything right. So this is already exciting, but it's also important to try in some a bit more complicated molecule. So we took the example of pyrimidine, nitrogen edge decay, right? From the picture here, it's difficult to see, but since we do some kind of atomic projection, it is important, since we have two nitrogen atoms, to localize the core. So in this case here, the core is localized here, and in this case, the core is localized here. The valence shell here has 2 and has 3. I don't localize, I don't touch them. I just use as they are. And here, very quickly, all the features of the experimental spectrum, they are more or less reasonably reproduced by the calculation. So I would say it is a reliable implementation. In this example here in the paper, we also compared what is the result of the one-center approximation and using the same RASPT and RASPT2 bound matrix elements with the code that Sergey presented in last Thursday. We also compute the brute force two-electron integrals, computed at the actual continuum. And the conclusion was that both the spectrums, they look pretty much the same. But this one that has this huge advantage of being simple, reliable, and you get directly from OpenMolcas, like you would get oscillator strengths. For example, you don't have to do much gymnastics to get this spectrum in this approximation. I will finalize, I will finish my presentation here with this example. It's a very interesting example using ozone. Ozone is a small molecule, but you have the three centers now because obviously for ozone, the decay is on the oxygen edge, but you have the oxygen in different chemical environments. So you see better now the localization that I said. So I'm using this notation of the OC for the central oxygen and OT for the terminal oxygens. And the ozone, because of these almost degenerate structures already in the ground state, so you have a very intense multi-configurational character on the ground state. And this is my half space. Here is not the Auger yet. This is this absorption spectrum to compare with the experiment. And here I highlight in the regions of the experiment where they set the energies for the measurement of the Auger. The Auger has these properties. Depending of the resonance or the initial state that you start, you have very different spectrum at the end. So the measurements are there, depending if you are here, where you are accessing the OT to the sigma star, or here that you are accessing the OC to the sigma star. But you also have a dashed line here, and this dashed line represents the ionization of the OT. So this is extremely interesting because you have overlapping the excitation from the OC to a sigma star plus the ionization of the OT. The spectrum, the experimental spectrum, it looks very much different. And okay, now plotting the results on top of the experimental spectrum here looks fine for this first example of the OT because there is no overlapping states. So the approximation here looks pretty much okay. It's a pity that you cannot see very well this top panel, but never mind. This is the resonant Auger to that OC transition. So at the beginning, all the properties, they're well reproduced, but when I get here, I don't see this strong and intense peak. But if I take the normal Auger of the OT ionized initial state, I see this peak very, very nicely and also some other features. But since the experiment is performed on the overlapping region with these two states, I can assume that I have same proportion, 50-50 of these two spectrums. So here I plot them and average both of them together, and what I see is a very nice reproduction of all the experimental, I mean, most of the experimental characteristics. That was all. So coming soon, the B-spline, I mean, the brute force implementation of these Auger two-electron integrals. I think it's important to have both because you decide which, if you need more details like angular distribution, so it's important to have the numerical solution. But if you're interested in this, also something that I'm working on is to couple the Auger spectrum with the trajectory dynamics to check dynamical effects on the Auger spectrum. It's important to have a simple, reliable, and cheap method because you have to repeat this several times. Yeah, thank you.
Thank you. Thank you very much. Yeah. We have time for a few questions. I don't see any questions in Zoom chat. Yeah.
Yeah, thank you, Bruno. I have a question. So how important is to describe the wave function of the electron in the continuum? Because this should be important, right, for low kinetic energy, small kinetic energy. But if you go to high kinetic energy, it shouldn't be that relevant.
Yeah, if you, for example, you can compute a XAS or XPS spectrum and use this sudden approximation that you neglect the electron in the continuum. But for the Auger, you cannot do something like that. You have to treat it because in that case of the sudden approximation, you consider that the integrals actually, they are not negligible, but they don't change much over the kinetic energy. But the two-electron integrals, because the Auger is basically a Coulomb explosion, something like that, and it changes a lot independent of the kinetic energy. So you have to treat it independently. Either you compute them brute force using this B-spline or whatever, or you do some one-cent approximation. But
so there is a dependence of the kinetic energy, even at high kinetic energy.
yeah, yeah. You cannot just neglect, not in the case of the Auger.
Okay.
Yes, okay.
Any further questions? If not, then let's thank Bruno again.